Okay, thank you everyone for joining a new lecture for Processing in Memory course. Today we have a very interesting lecture about a prototype of an end-to-end processing using memory system. Remember that in previous lectures we have been discussing several processing near memory architectures that already exist in the real world, but we didn't talk in a lot of detail about processing using memory architectures, and the main reason is that there are not yet commercially available processing using memory systems. The closest thing that you can find today is something like this prototype PyDRAM that Ataberk is going to present. Ataberk is a PhD student in the Safari Research Group, and he's doing research in processing in memory, DRAM, memory systems, and many more things. I believe that this PyDRAM work is very interesting for those of you who are interested in processing in memory, and in particular in processing using memory. And I think that this prototype and this framework can enable much more research in this direction. So Ataberk, thank you very much for your lecture today. Feel free to start whenever you're ready.
Yeah, thank you for introducing me, Juan. So I'll get started right away. So the title of our work that I'm going to present today is PyDRAM, a framework for end-to-end integration of processing using memory. And you can see the authors in this paper in the list below. And as you can see, Juan is the second author for this paper. He has helped a lot to develop the work. So we are both experts in this, and then we will be glad to answer your questions. So I'll start with an executive summary. We're motivated by recent works that propose in-DRAM computation primitives with great potential to improve performance and energy efficiency of computing systems. However, we see that these works are usually developed in limited environments, such as simulators or characterization platforms, specialized characterization platforms, where many parts of the system are ignored. And thus, the challenges in integrating these techniques into a system cannot be fully explored in these limited environments. And our goal in this work is to develop a flexible platform to explore end-to-end implementations of current and future processing in memory techniques. And our key idea is to build an FPGA-based infrastructure that supports in-DRAM operations and has system software support. This is the outline of this presentation. I will start with some brief background on DRAM. And here is basically a processor's memory controller. It communicates with a set of DRAM chips on a DRAM module through what's called a DDR interface. And each DRAM chip contains multiple banks. Inside the bank, there are multiple subarrays, and subarrays contain multiple DRAM mats. And these DRAM mats are separated from each other by word line drivers and sense amplifiers. Inside the DRAM mat, we have multiple DRAM rows, and inside the row is a number of DRAM cells, and a simplified version of a DRAM cell looks like this. Now we will see how we access this DRAM cell. This is a diagram showing how a DRAM cell is connected to a sense amplifier, and it contains two components. The capacitor stores data as charge in the capacitor, and the access transistor determines if the cell is being accessed. And this access transistor is controlled by the word line, which we enable to connect the DRAM cell to its bit line. And the bit line bar is essentially the inverse of the bit line. And the DRAM sense amplifier has an enable signal, which determines if the sense amplifier is currently active. So we will see how we access this DRAM cell. And initially, both the access transistor and the sense amplifier are disabled, and both ends of the sense amplifier are maintained at half VDD. And in this example, the capacitor is fully charged. So to access the cell, we first enable the word line, and this will connect the cell to the bit line, or the capacitor to the bit line. Now, since the capacitor is connected to the bit line, it will start to lose charge. It will share its charge with the bit line. And this will result in the bit line voltage to deviate slightly towards VDD. When we enable the sense amplifier, it will compare the voltage difference of bit line and bit line bar, and amplify the deviation until bit line voltage reaches VDD. And since the capacitor is still connected to the bit line, this process also restores charge back to the capacitor. And now we will look at how DRAM operates at the scope of a single subarray. And because memory controllers typically access DRAM cells in the granularity of a cache line or a cache block, we combine consecutive DRAM cells in this diagram to form cache lines. So in a single row, we will have multiple of these. And on the bottom, we have a timeline of DRAM commands. First, we will activate the first row to essentially copy its data to the sense amplifiers. And at this point, we can read data from the sense amplifiers by sending read commands. If we want to access another row, we must first pre-charge the DRAM bank, which will close the open DRAM row and set the bit line voltage to half VDD such that we can perform another sensing operation. We can now activate the second row before we read data from it. And to ensure correct operation in DRAM chips, we must obey certain timing parameters that are defined by manufacturers commonly, and these define intervals between DRAM command pairs. Two important timing parameters for our work are TRAS and TRP. TRAS is the time required for the charge to become restored in the capacitors on the open row, and TRAS dictates the amount of time we need to wait between successive activate and pre-charge commands to the same DRAM bank. TRP is the time it takes for a bit line to become pre-charged to half VDD, such that we can send a new activate command to the DRAM device. And successive pre-charge and activate commands must be separated by a TRP amount of time on the command bus. Now I will briefly describe existing processing using memory techniques. So processing using memory techniques take advantage of operational principles of memory to perform bulk data movement or computation inside memory chips. And these techniques can exploit internal connectivity. In the previous slides, we saw how DRAM cells are connected to the sense amplifiers, and this point is essentially referring to that internal connectivity means that there is some way to move data inside the DRAM chip from one location to another location. And these techniques can exploit analog computation capability. And the examples to these are, for the internal connectivity would be RowClone, and for the analog computation capability would be in DRAM and OR operations or DRange to generate random numbers. And here are some pointers to these works. I won't go into detail about how they do everything, but we will talk about RowClone specifically because that's something we evaluate in our work. So I will start by motivating RowClone using this animation here. On the left side, we have the processor, its caches, and the memory controller. It is connected to this memory module on the right or a memory channel. So normally, when we want to copy data from the source page or source block in memory to the destination block, what we will do is we will bring data from the source block in cache block granularity first to the memory controller, and then to the caches, and then to the core. And once we have it in the core, we will create essentially a copy of it. We will store it to some other address, and this will first be stored in the caches, and then over the memory controller, it will go back to the DRAM module on the right. And this process actually incurs high latency. It takes around 1 microsecond to copy 4 kilobytes or a single page. And it also induces high energy costs. And the key idea of the RowClone is basically, can we reduce these overheads if we are able to do the operation in DRAM? So we don't want to move data out of the DRAM chip. We want to do it in place. And this is the key mechanism RowClone develops. It's one mode of operation of RowClone. There are multiple ways that we can use RowClone to reduce data movement, but I'm going to talk about only the full parallel mode, which does copy operations inside DRAM subarrays. And now I will explain how we do that. So we have seen the organization of DRAM in the previous slides. This is another view of it. So we have a single subarray here. On the bottom, we have the row buffer or the sense amplifiers. and the cells here form DRAM rows. So we have the source row and the destination row, and what we want to do is to copy the source row to the destination row. We will do this in 2 steps. First, we will copy the source row to the row buffer or the sense amplifiers, and to do this, we already know that we can use activate command. When we activate the DRAM row, the data will be copied to the row buffer. And the second step is to copy this data back from the row buffer to the destination row. We know that we can do step 1 in current DRAM chips. It's already supported, but it's unclear how we can make a minimal amount of changes to support step 2. And now I will describe how RowClone proposed doing it, the key idea of RowClone full parallel mode. Here we have 2 DRAM cells on the same bit line connected to a sense amplifier, and we want to copy data from source cell to the destination cell. And initially the source cell is charged to VDD and the destination cell is 0, and the bit line is pre-charged. So first we will activate the source row to connect the source cell to its bit line, and this will start the charge sharing process, and then the bit line voltage will deviate toward VDD. And then the sense amplifier will amplify this difference so that both the source cell gets restored, gets its charge restored, and the bit line reaches VDD. Now at this point, what we want to do is we want to disconnect the source row from the sense amplifier, and that's what we do in this step. So when we do this, essentially it's half of a pre-charge operation. We have closed the open row, but we didn't start pre-charging the bit line. So the bit line still has the value of the source row, essentially. And next, we only need to connect the destination row to the bit line. And once we do that, because of charge sharing, the bit line, since the bit line has a higher capacitance, it will essentially fill up the destination row quickly. And then this is how we do the RowClone full parallel mode copy operation. And essentially by doing this, we have enabled fast bulk data copy with very small overheads. We only need to be able to disconnect the row and not start the pre-charge process on the bit line. And another potential processing using memory technique that I talked about, that I introduced, was in the bitwise operations. And there are prior works that show that this can be done at low cost using inherent computation capability of DRAM. And the idea is to essentially activate multiple rows at the same time to perform computation. And these works show that we can improve performance energy by 30 to 60x. And here's a paper to take a look at if you're more interested in these. But I will also briefly describe the key idea of this paper, basically. And here I will show you how we do in DRAM and the NOR operations using what's called triple row activation. Here we will simultaneously enable 3 rows to perform some computation on the bit line itself. And here we see A and B, cells A and B are charged to VDD, and cell C is discharged. We have the same bit line as the previous diagram here, and the bit line is initially pre-charged to VDD, half VDD. What we'll do is we will activate all these cells, activate all of the rows at the same time, and all cells will start to share their charge with the bit line. And after some time, some cells will lose the charge. The cells that are charged will lose their charge, and the cell that was not charged will gain some charge. And this will cause some deviation on the bit line, and then this will be amplified by the sense amplifiers, and then the charge will be restored as we have seen previously. Now, if we take a deeper look, we will see that this final state of the bit line is essentially this Boolean formula here: AB or BC or B or AC. And if you simplify this a bit, you will get to this formula. And if you if you fix the value of C, meaning that either you fill C with a Boolean value of 1 or 0, you will see that you can realize two Boolean functions, which is A or B on the first part here, or A and B in the second part here. So this is the key idea of the both bitwise and NOR in DRAM works, basically. And then a more recent work showed that these operations are possible, or these operations are well supported by real DRAM chips. The work's name is Compute DRAM, and you can see a link on the bottom of the page here. This work demonstrated row clone, full parallel mode, and bitwise and NOR in real DRAM chips. And the way they do it is they violate the two key timing parameters, TRAS and TRP, and this induces undefined behavior in the DRAM chip. Here is the name of the authors in the paper's full name. And I will describe how this paper, how the proposed methodology in this paper does row copy in real DRAM chips. It's very similar to the key idea of row clone and key mechanism of row clone. Here is a diagram of the state changes on a single bit line over time on the x-axis. So we have, similar to previous figures, we have one cell here, another cell here, and the sense amplifiers on the bottom. And on the very bottom, we have the timeline. So initially, we have in the first cell a value encoded as 1, and the bit line is pre-charged. What we do is we send an activate command to access the cell and copy its value to the sense amplifier. And then next, we will wait for some time, T1 amount of time. This is essentially the TRAS that we violate. And then we send the pre-charge command. Now, when we send this pre-charge command, two things will happen. First, the open row will be closed, and the bit line will start to deviate towards half VDD. So bit line will start to become pre-charged. But before the bit line is fully pre-charged, we send another activate command after a T2 amount of time. And as you can see in the diagram, the bit line will be closer to half VDD, but it will still have some excess charge because the pre-charge process was not complete yet, because we violated timing parameters. And the second activate command will enable the second row. And since the bit line still has some excess charge, this will overwrite the value that was in the row that we just activated. So we have done the copy operation the way essentially row clone proposed, but by inducing undefined behavior. And this is what I already described. So if you're more interested in these works specifically, you can take a look at Professor Mutlu's lecture on processing using memory. You can find the link on the bottom of this page here. And also you can take a look at one of our recent live seminars where Nastan presented a SIM-DRAM, which is, again, another processing using memory technique. And finally, I want to talk about the rocket chip SoC generator, again, another tool that we've used in developing PyDRAM. It is an open source SoC design generator. SoC is a system on chip. It has many components that form your common computing system, essentially. It is composed of many SoC generators, and a generator is essentially a hardware construction code, a chisel or Scala code that builds hardware. So in this rocket chip generator, we have multiple of these generators that are responsible for building cores, caches, in a configurable way. We will be able to configure very few lines of code to generate very different architectures or systems. And you can see some of the parameters you can enable or disable by just changing one line of code on this diagram here. And finally, the system that was generated with this chisel and Scala code will be output as synthesizable Verilog RTL that you can use to build your chips. You can use to prototype on FPGAs. you can do all sorts of simulations and analysis on it. Okay, now I can talk about PyDRAM if you don't have any questions regarding the previous topics that I discussed.
Yeah, I think you can continue, Ataberk. I don't see any questions in the chat.
Okay. Yeah. So I will reiterate on our goal here because I think it's been 20-ish minutes and people might have forgotten, but our goal is to develop a flexible platform to explore end-to-end implementation of the PIM, these processing using memory techniques that I described. And to do that, we want to enable rapid integration of new techniques by providing some key components. On the hardware side, as these key components, we have an easy to extend memory controller so that people can, or the developers can integrate new techniques more easily, and an ISA-transparent processing using memory controller so that we can provide a general or a flexible controller that is portable to many different architectures. And on the software side, we have an extensible software library that developers can easily add more functions into if they want to support a new processing using memory technique, and a custom supervisor software that supports the bare minimum system functionality like memory allocation, memory management, memory alignment support, basically. I will talk about the memory controller first. So since the processing using memory techniques, the real ones that I described require issuing DRAM command sequences with violated timings, we develop an extensible memory controller that facilitates implementation of such techniques through modular design. And what I mean by that is new command sequences require essentially the minimum amount of changes that the developers can easily replicate the existing code to complete. And specifically, this will require adding new state machines and our implementation. And we implement 3 submodules to further ease this effort of integrating new stuff and using the platform essentially for development purposes. And the first one is the periodic operations module, which performs periodic refresh and bus maintenance operations to keep the DRAM bus in a valid state, and the DRAM cells refreshed. And the second component is our scheduler, which schedules normal or regular DRAM read and write operations and applies a simple open bank policy. And the third component is the configuration register file, which stores timing information about the command sequences that need violated timing parameters, and it can be accessed using load and store instructions from the CPU. The next component is the processing using memory controller, or PIM operations controller, and it provides ISA transparent control for PIM operations, and it's hierarchically it is connected as a memory mapped module to the rest of the system, and it resides in the memory controller in our current version. And this diagram is depicting in the blue rectangle. You see the PIM operations controller module. It has a simple interface. It can the user can offload 128-bit instructions to it. It has multiple memory map registers, so the user will, or the libraries we have developed will use store instructions to configure these registers to initiate processing using memory operations and retrieve data, the results of these operations from the PIM operations controller. And we currently implement 5 instructions. Here are these instructions. We have 1 instruction for row clone operations, 1 for inducing activation failures, which we use to generate random numbers, which I will describe next. And again, the 2 remaining functions are related to instructions are related to random number generation, reading the random number. We have one instruction to read the random number. We have another instruction to read the random number buffer size, where we keep the random numbers, where we store the random numbers after generating them periodically. And the final instruction is to write to configuration register file that I described in the previous slide. We have many reserved bits, as you can see, for other commands, and the instruction size is configurable in case we run out of bits, or we can use a smaller encoding for better performance. So on the software side, we have first software library. We call it PIMolib. It's exposes PIM operations to the user while abstracting the hardware implementation details. And what I mean by that is we decided to implement the communication between the PIM operations controller and the CPU using memory map interfaces, but this can be changed in the future, and new ISA instructions could be used to do this, to perform the communication. And in that case, this library would abstract such details from the user, and it also provides template functions for users to extend when they develop new PIM techniques on PyDRAM. So this is what one function in this library looks like. It's a copy row function that we use to perform row clone operations. And here on the so it's essentially separated into two stages. In the first stage, we prepare an instruction. We have a 128-bit instruction, and we fill up the fields according to the encoding. And then in the next part, we offload the instruction and then block execution until we are acknowledged by the PIM operations controller. We can choose not to be acknowledged. In that case, we wouldn't block, and that's optional. And there are examples of that in the library. And then the final component is the custom supervisor software. And this was selected and developed with the goal of being simple and easy to hack, such that new system support for new PIM techniques can be implemented easily. And it currently has support for virtual memory management and some memory allocation. And this is based on the RISC-V proxy kernel. And we have set as future work integrating PIMolib into Linux so that we can provide a full operating system instead of a simplified supervisor software. I'll describe the execution workflow of a copy operation using PyDRAM's hardware and software components. And this diagram is an extended version of the previous diagram, basically. The first step, we will the user application will interface with the OS and perform system calls to ultimately perform a copy operation. And the OS will use the PIMolib functions to convey this information to the POC using store instructions. And then the fourth step, the processing PIM operations controller will oversee the execution of a PIM operation. And by overseeing, essentially what I mean is just bookkeeping and controlling the execution within the memory controller. And then finally, the scheduler and the memory controller will arbitrate between three different inputs, which can come from the memory bus, regular read and write commands, processing using memory controller, which would be the copy operations and activation latency failure operations, or the periodic operations module, which will send calibration operations or refresh operations. And we developed the framework on a prototype using the ZC706 board. And inside the board, the system we have prototype has a single core RISC-V Rocket CPU clocked at 50 megahertz. And it's an in-order single issue, very simple CPU with 16 kilobytes of L1 cache and 4 kilobytes of instruction cache. And here you can see the DRAM module under the cage. This is what we use to perform the processing using memory operations. And on the FPGA, we have implemented the RISC-V system. Okay. I'll again wait for a few seconds to take any possible questions here. Okay. So I will continue.
No questions in the chat, Ataberk. Thank you.
Okay, thanks. So I'll continue with our case study where we implemented RowClone, integrated it end-to-end in our prototype, and then performed some evaluation studies. So I'll first start by presenting you the challenges of implementing RowClone in a real system. And primarily, these are memory mapping requirements. So the first requirement is what we call the alignment requirement. And this states that the operands must be placed at the same offset to their respective DRAM rows. And this figure explains it better, I think. So since source 1 and target 1 are offset at different positions, we won't be able to copy source 1 to target 1 because their bit lines are not aligned. By doing RowClone FPM operations, we cannot copy this data to the other data. From this location to the other location. The second requirement is what we call the granularity requirement, and this states that the operands must occupy whole DRAM rows. And the problem is basically for this second case where we have source and target to align, but they don't occupy their respective rows. They don't fully occupy their respective rows. What can happen is there will be some data in the row that source 2 is mapped to. And this will overwrite the data that target 2 is mapped to in this rectangular location I'm highlighting. And that's something we don't want. It's a side effect that we need to avoid. And the third requirement is what we call mapping. And this states that the operands must be placed within the same. We don't share the same set of sense amplifiers anyways, and we cannot copy data using sense amplifiers the way I described in the earlier slides inside DRAM chips. So it won't be possible. And when the fourth case here, the first three I already described. The fourth case here, when the allocation satisfies all three constraints or all three requirements, we can perform RowClone operations correctly. And this is one challenge. So to solve this challenge, we develop a new allocation mechanism, and I will describe this one next. This allocation mechanism that we developed satisfies the three requirements that I talked about, and it's called alloc-align. And what it does is it tries to optimize physical address allocation to this array here for size byte large copy operations, so that RowClone can be used most effectively. And this will become more clear as I go on. For example, when we want to bulk initialize some data with zeros, we can place a row full of zeros in a DRAM bank and allocate accordingly to make sure that we can initialize data using RowClone. And we have 8 kilobytes of data, and our rows are 8 kilobytes in this example. Then we can just, we need to map this full operand to a single row to be able to use RowClone operations. And alloc-align will try to optimize allocations of arbitrary sizes such that we can initialize these operands with RowClone operations most effectively, using them for the majority of the data. And the key idea we have in providing such a allocation mechanism is basically today's systems usually have 2 layers of translation within program observed addresses, the virtual addresses, and physical DRAM addresses. And we see that the OS has full control over the virtual to physical address translation, but it does not have any control over the physical address to DRAM address mapping. And the idea is if we can control this mapping from virtual address space to physical address space, and we know how the physical address space to DRAM address space mapping looks like, we can implement a local line. And that's our assumption. So we assume that we know about this mapping. So how does it work? This is, again, describing the semantics of the function. So it will take an argument size, how many bytes we want to allocate, and it will return a pointer. So how does it lay out an array to DRAM? It will first distribute the arrays over multiple banks while occupying DRAM rows as fully as possible, and then fall back to malloc for the remaining data. And again, reiterating on the assumptions we make here is that we know the DDR address mapping, the DRAM address mapping in our system, which means that we know which bits in the physical address maps to which bits in the DRAM row bank column addresses. And fortunately, we can reverse engineer this using by checking for row clone operations. So if we have two physical addresses, we can check if a row clone operation between them succeeds, and then we deduce the information that they are in the same subarray physically. This will help us decode the address scheme to some extent. And to further decode the address scheme, we can use RowHammer we can use RowHammer attacks to find out find the neighboring rows to a DRAM row. And there are other techniques that we can use to reverse engineer DRAM mapping. And the second assumption is based on the first assumption. Basically, we know which DRAM rows are in the same subarray, and then we can do this by, again, checking for row clone success rate, which I described in the previous assumption. And we develop other versions, specifically one other version of a local line, which we use to implement row clone copy operations. So we need to allocate. Two arrays in the same subarray. In this case, we extend the definition of a local line with another parameter called ID. And what this will do is, if two different local line calls are made with the same ID, the local line will allocate these arrays in the same subarray. Now I will describe the address mapping we have in our system. So since we developed the memory controller, we have full essentially autonomy over the address mapping we use. And this is the module that we use. This is relevant because I can show you the number of rows, banks, and columns we have. Since we have 16K rows, we have 14-bit row addresses. Since we have 8 banks, we have 3-bit bank addresses, and similarly 10 column address bits. And this is what the physical to DRAM address mapping in our system looks like. And again, this is configurable. We have on the highest, the most significant bits we map to DRAM rows, then banks, and then columns. Now I will describe how a local line works over an example. So here in this example, we have two arrays, A and B. We want to map these into the same subarray such that we can copy from one to another. And these arrays are size 16 kilobytes in this example. And here are multiple DRAM banks and 2 rows depicted in the same subarray. What a local line will do is it will scatter contiguous virtual pages into multiple banks to enhance bank level parallelism, and also make sure that the 2 arrays can be copied to each other using row clone operation. And to do so, it overlaps the virtual pages of 2 arrays that are at the same offset and the same in the same DRAM bank. And to support this operation, we implement 3 structures. The first one is called subarray mapping table, and this is a table that collects DRAM rows that map to the same subarray under the same entry. And here it has as many entries as there are subarrays in our DRAM module in all banks. So an entry looks like this. It has first some metadata, number of free rows in the entry, and then we have M pairs, and each pair is 2 physical addresses essentially, and all the pairs in this entry will point to DRAM rows. All the physical addresses in these entries will point to DRAM rows that are in the same subarray. And here we assume that the DRAM row to subarray mapping can be arbitrary, meaning that subarray 0 could have DRAM row 0, 15, 37 mapped to it without any discernible pattern between the addresses. And another subarray could have row 13, 22, and 156 mapped to it. And this doesn't really affect how our mechanism works. And we reserve one entry in this, we reserve one pair in every entry for initialization. We reserve the last entry and we allocate the DRAM row that this entry corresponds to with zeros. And later we will use this for zero initialization using row clone operations. The second structure is the subarray ID map. And this essentially maps from page numbers to subarray indices. Here we see how the table looks like. We have all the physical page numbers as indices and the corresponding subarray ID, the physical. So basically, the subarray that this physical address maps to on the table. So I will show you how we use the subarray mapping table first for an alloc-align operation. So first, we will find how many banks we need to utilize, and this will you can find this by dividing the number of the number of bytes you're allocating to how much data you can map to all rows, all banks in one row. So basically, size divided by number of banks multiplied by row size, and then we will spread the allocation across this many banks. And we will first split the array that we're allocating to 4 kilobyte blocks. And we split this into 4 kilobyte blocks because it's a page size. It's the same as a page size in our system. And we have the parameter NB, which is the number of 4 kilobyte blocks of this array. And we loop over all of the elements in AI, in the array A. We pick a bank for this to place this page in, and then we select an SAMT entry with more than one free address pair. So what we're trying to do here is we're trying to find a correct place to map this 4 kilobyte page into. And then we select one pair that's free from this entry, and then assign physical pages in the pair to virtual pages AI and AI plus NB over 2. And here's a diagram that depicts this specific operation. So the reason why we iterate only to half, essentially the middle of this array, is because with in every iteration, we map 2 virtual pages of the array to a single row. Because a row is sized 8 kilobytes, we can fit 2 virtual or physical pages to a single row. And what it will do is something like this. So we will fit A0 to the same row as ANB over 2, and then we will move to the next entry. So we will select another DRAM row, and then we will put A1 and ANB over 2 plus 1 to that row, and then we will move on to the next page. And now I will describe how we, after we allocate using alloc-align, how we perform a row clone initialize operation. And this is basically using row clone to bulk initialize data. And this semantics of the function looks like this. So it will take a pointer to the array that we want to bulk initialize and an argument n, which defines the number of, or the number of bytes we want to initialize with 0. So we'll first split A into 4 kilobyte blocks again. And this means that we have the virtual address range of A, and we just split it into 4 kilobyte blocks, we traverse that virtual address range in 4 kilobyte increments. And for all blocks, we will translate from AI to AI is a virtual address to its physical address, PA1. And we will use this as the destination address because this is the address that we want to bulk initialize with zeros. And then we will access the subarray ID map, which holds physical address, which stores the information of which physical address is mapped to which subarray. And we will retrieve the subarray ID of this physical address. And then later we will access the SAMT to get the address of the all zero row that we reserved in every entry for this subarray. And this we will call PA0. And then the only thing that's left for us to do is to perform a row clone operation from this physical address with all zeros to PA1. And because there are two virtual pages or physical pages in a single row, doing this will copy zeros to this address also, this part of the array. I hope that's clear. And this is the end of the first, well, the allocation mechanism, essentially, the description of the allocation mechanism we developed. And maybe I'll pause here also in case there are questions.
There are no questions in the chat. I have a couple of questions for you, but I prefer to ask them at the end.
Okay, that works. So, yep, then I will move on to the next challenge, and that's memory coherence. So since we operate on data in DRAM, and like all the PIM techniques have this in common, the data that must be up to date, essentially on DRAM. But since we employ also caches in today's computing systems, this data might also be cached in the current programming model. And then we have to make sure that we maintain coherency. So we don't want to operate on stale data, or we want to develop mechanisms that enable us to maintain coherence regardless if we're operating on up-to-date data or not, which is not provided in current computing systems. So one way to do this, one way to guarantee coherency is to use cache line eviction operations or CL flush operations, and make sure that basically every cache block of the data that we're copying is up to date in DRAM. So we will evict the dirty copies of the cached cache blocks, meaning that cache blocks that reside in CPU caches, not in DRAM, basically. And what we do is we implement this operation in RISC-V Rocket. By default, it's not supported, or it was not supported. I don't know if currently the RISC-V ISA has these instructions yet. And the advantages of implementing it this way is that it's realistic because this is what's used in many of the contemporary processors. As far as we know, this is used in this is basically what's used to maintain coherence in current computing systems. And since we use these operations to first evict all cached copies of the data that we want to copy, we can still access the data and keep cached copies of the data when we're not doing the computation in DRAM. And when we want to do the computation in DRAM, we will just use CL flush first. The overheads are, well, the disadvantages are that this is a very high overhead mechanism. We will need to execute one instruction to evict one cache block. And we will have to execute this instruction for every cache block that belongs to the data that we want to copy in DRAM. This is what we implement in PyDRAM, but there are other mechanisms that can be studied in the future using PyDRAM. So one mechanism, dirty block index, I will briefly describe it. It helps us alleviate the instruction overheads of this of the memory coherence management operations or CL flush operations by keeping track of the cached copies that belong to a DRAM row. So the observation here is that not all cache blocks in a DRAM row will be actually cached physically in CPU caches. By keeping track of the parts of a DRAM row that is actually cached, we can execute the CL flush operation only for those cache blocks. So we will skip the CL flush operations for the cache blocks that we know for sure that don't reside in CPU caches. And that will help us reduce the overhead of these operations. Another potential mechanism is to perform regardless of coherent state of the cache blocks, meaning that if they're up to date in DRAM or not, we perform the operation. And then later, if we figure out that we have operated on stale data, we will roll back the operation. And this is described in more detail in this paper that I link below. It's called lazy PIM. And also, I think Conda is a more recent version of the same paper. I can link it in the updated slides, maybe. Now I will describe the how we evaluated the row clone case study. Here you can see the system configuration we have. I already talked about the CPU, and we have 4 entry TLBs. The data cache you already know again. The memory we use is a 1 GB DDR3 module. It's clocked at 400, the command bus is clocked at 400 megahertz, which means that we have 800 million transfer bandwidth. It has a single rank and row size is 8 kilobytes. We test 2 configurations of row clone support in our system. The first one is bare metal. We don't do any sort of address translation. And the second one is what we call no flush. We have system software support, but we assume that the data is always up to date. So we will never use cache line flush operations here. So for workloads, we use 2 micro benchmarks, CPU copy and row clone copy. CPU copy will copy an arbitrary amount of data using load and store instructions, and row clone copy does it in DRAM, the way we described. And from spec 2006, we only evaluate lib quantum because we had problems executing the other ones. We don't have enough system support to reliably run the other benchmarks, essentially from the workloads from the spec suite. So the first thing I want to show is the copy throughput improvement we have for bare metal, the bare metal configuration. And in this figure and the figures that I will show you, on the x-axis we will have the array size ranging from 8 kilobytes to 8 megabytes. This is the size of the array that we perform the copy operation on. And on the y-axis we have the throughput improvement compared to the CPU copy that we achieve using our row clone copy operations. And here the takeaway we have is row clone copy can provide over 365 times performance improvement over Rocket's CPU copy. And then we have the same results for the no flush configuration for both row clone copy operations and initialization operations. And again, the baseline here is the CPU copy and initialization operations for the 2 bars. So RCC is where we do the row clone copy operations, and RCI is where we do the bulk data initialization operations. The X and Y axes are the same. And the takeaway we have here is that copy and initialization operations, even with system support, improve throughput drastically by 119x for copy operations and 89x for initialization operations. And then we estimate the overheads of CL flush in our implementation. So on the y-axis, we still have the throughput improvement of copy operations provided by row clone copy operations over the CPU copy operations. Again, 2 bars for initialization and copy operations, respectively. And on the x-axis, this time we have the proportion of the proportion of cache lines that are dirty, meaning that they are their updated copies reside in the caches. So on the leftmost side, we have 0% dirty. this means that none of the cache blocks that map to this row are updated. They have updated values and caches. And this essentially means that we don't have to write back the data from the flushed cache lines to DRAM. The difference between 0% dirty and 100% dirty here is that for 100% dirty, we have to write back all the cache blocks to DRAM. Regardless of the proportion of dirty cache blocks, we execute one CL flush operation for every cache block in the 8 megabyte large data that we copy in this figure. And we see that CL flush dramatically reduces the potential throughput improvements that row clone copy operations can provide. And we make the final remark that PyDRAM enables the study of better coherence mechanisms. So it could be worthwhile to study those and evaluate them using our infrastructure in the future. Now I'll summarize what we have talked about in the evaluation side. So PyDRAM can run real workloads, the infrastructure as is, end to end, using new processing using memory techniques. So to demonstrate this, we have run libquantum, and what we did in libquantum was we replaced calloc or calloc calls with allocaline and row clone initialization. So as you know, some of you may know that calloc is used to zero allocate some data. So the difference between malloc and calloc is basically malloc just allocates you some data, and calloc allocates it first and then makes sure that that data is zero, initialized with zeros. And we have seen that, like, after doing this, we saw that we can improve the performance of libquantum by 1.3%. And the reason for this is this small improvement is essentially there's not many of these replacements that we can do. And the data that we bulk initialize is small compared to the whole execution of the program. It takes small amount of time to begin. And you can find the details in the paper on arXiv. We've seen that row clone can greatly improve bulk data copy performance with and without system support. And we've seen that it requires efficient coherency mechanisms to achieve its maximal copy throughput improvement potential. So now I will list some potential case studies that we can do using our infrastructure. We already implement row clone and derange, and there are other works that we can evaluate. So the two works that I list here, Ambit and SimDRAM, have similar design challenges or integration challenges, similar to row clone to some extent. We have to think about memory allocation and alignment for these mechanisms. We have to think about coherence again. And for SimDRAM specifically, we have to think about how to efficiently transpose data, because SimDRAM operates on a bit serial layout. It has to transpose data first before it writes it to DRAM and operates on it. And that's another thing to think about. And other sets of works, I listed DLPUF and QuackTRNG. DLPUF is a physically uncallable function in DRAM using reduced activation latency. And QuackTRNG is a true random number generator that generates random numbers by simultaneously activating 4 DRAM rows. And these both have the following challenges, like memory scheduling policies, so that we can efficiently perform both regular memory reads and writes and these physical unclonable function and random number generation operations at the same time. So memory will become an even more shared resource if we want to implement these techniques. And both of these techniques require post-processing, and post-processing can be done in the memory controller, but we need to think about how to do it best, how to efficiently perform it. And we talk about more potential case studies in our paper. If you're interested, please check it out. And finally, we compare it to other platforms again, in greater detail in the paper, but to sum up, these existing platforms don't provide an interface with the real DRAM, or basically they don't satisfy all of the 4 properties at the same time. That is, the first one is interfacing with a real DRAM device. An example is simulators. You can't use real DRAM devices integrated with simulators. They don't provide a flexible memory controller design that can be easily modified to implement new techniques. They're not open source, so we cannot build on them to begin with, or they don't have support for system software. And with that, I actually finished the slides. Now I will close up with an executive summary again. So we were motivated by recent works that propose in-DRAM computation primitives with great potential to improve system performance and energy. And the problem we stated was that these works are developed in limited environments, and because they're developed in limited environments, we have to ignore key components of the system, and we cannot explore the challenges of integrating these PIM techniques into a system in these platforms or tools. And our goal is to develop a flexible platform to explore end-to-end implementations of current and future techniques. And our key idea was to build an FPGA-based infrastructure that supports in DRAM operations and has system software support. And that's the end of it, basically. I can thank you for listening to me, and I can take any of your questions if you have.
Okay, thank you very much, Ataberk, for the very good lecture. I don't see any questions in the YouTube chat, but I want to ask you a few questions myself.
Yes.
Yeah, I mean, I think I'll go from the beginning of your slides. You don't have to go back unless you find it necessary. So my first question is, because you mentioned what's the FPGA that you used for the rocket chip and implementing the framework, and you mentioned one a specific model of Xilinx. Do you think? Yes. So how difficult is to port PyDRAM to another FPGA, assuming that someone might have access to different FPGA boards?
Yeah, so that's a good question, because it relates to all the flexibility arguments I made, like this being an easy to use platform. And one part of that is to make sure that it's easy to port to different FPGA boards, because with time, some of the boards will be like obsolete, and that's one of the concerns we had. So I think it's quite straightforward, actually. We make use of open source hardware that is basically being actively developed by a huge community. So they are already porting the hardware that we use in our prototype to new boards as we speak, probably. That's basically the RISC-V system that I'm talking about. And basically, I will talk about other components and how we can port them, and then I hope we will have an idea of how easy or hard it is to port to a new platform, essentially. And then the next thing we have is the memory controller. And in the memory controller, we make use of Xilinx's IP to actually realize the physical connection to the DRAM device. And that is, again, something developed by Xilinx for every generation of their FPGA boards. I think similar IPs exist for other vendors. I'm talking specifically about Xilinx because I think that's more common to find than the Altera boards, or if there are other FPGA vendors, maybe for them also. And the idea there is we have a standardized interface with that IP. So the new IPs also support either the same interface or a very similar interface. And then you will only have to implement take the code we have, wrap around with some new constraints that define the PIM mappings for the new FPGA board. And then you have your prototype on a new board, essentially. There was another point maybe I wanted to make that I forgot. But I guess the short answer is it is easy. The long answer is maybe the one that I gave just now.
Okay, I mean, the thing is that it's feasible. Of course, there is might be some constraints to take into account, and probably some small issues to solve. But it's like let's say relatively straightforward to use a different FPGA.
I think so. Yes.
Okay, that's very good.
Yeah. So the other thing I wanted to talk about was, I guess, the Open FPGA initiative. Maybe it's not an initiative anymore, but it's like a mature thing at this point. Basically, you can use this software that people have developed on GitHub to basically develop stuff for FPGAs. We have open memory controllers, open anything else, and one thing to do maybe in the future could be to port it to that infrastructure, essentially, and then we have potentially another we have potentially less portability issues. Anyways, I guess I want to talk about that.
Mm-hmm. Okay, yeah, that would make sense. It would be a good idea for the future. Mm-hmm. Okay, yeah, I would like to ask you another question as well. So now that we are in this slide, I mean, it's kind of a double question. First is related to the fact that the RISC-V CPU is single core. So I guess this must be related to the amount of space that you have, the amount of resources that you have in the FPGA for additional cores. But assuming that someone has access to a much larger FPGA, would it be possible to have multi-core? That's the first part of the question. The second part relates to the bandwidth. Not the bandwidth, the frequency. That is also like relatively low, right? It's only 50 megahertz. And while it should be possible to access data from DRAM at a much higher frequency, right? And my question here is, I would like to connect this question to a previous lecture that we had in this course. It's about the AXDIM system. Remember that AXDIM has places at FPGA, well, a reconfigurable fabric of some time near the ranks, the memory ranks on the DIMMs. And one thing that the authors of that paper did in order to kind of obtain realistic performance measurements was to scale down the frequency of the system, right? So I was thinking, while listening to you, I was thinking, would it be possible to apply a similar strategy here in this 5 DRAM platform, like for example, reducing the DRAM frequency heavily?
Yeah. So there are essentially three questions. The first one was if we can fit more cores or larger cores to like a newer FPGA or a larger FPGA. The second is if we're bound by the frequency and how that exactly is a problem, or if that's a problem. So thank you for these questions. Again, these are important, I think, to address to some extent, hopefully. So definitely, if we have larger FPGAs, we can fit more cores. I think Rocketchip already supports implementing multiple cores. So it would be possible, I think, either larger cores or the same core, but many more of them is possible. Basically, we can extend PyDRAM with that, or PyDRAM prototypes with more cores can be developed. And the second question is how much of a problem is frequency? So I think without like maybe it's not applicable to every scenario, but in general, FPGAs will result in lower frequency than ASIC for sure. And these CPU implementations or processor implementations suffer from that and on the FPGA. So I think this is what we could clock. The system we have at maximum was around 50 megahertz. As far as I remember, we tried with 100 megahertz and it failed for this FPGA board. Better FPGA boards or bigger FPGA boards might have more slack, but a realistic upper bound to frequency, I think, for these open source processors at least would be, I don't know, in the range of 200-300 megahertz. And then you have this problem of not simulating or, well, not representing a real system. So your memory is faster than your processor. And I guess you mentioned how IEDM solved this issue by scaling that bandwidth. That's possible. I think that's a good method, at least, better than nothing. Basically, what you do is you try to scale down. I hope I understood this right. You scale down the throughput of the memory such that you your system represents a more realistic CPU to memory throughput ratio or frequency ratio. That's something we didn't do in PyDRAM, but doing that could be, I guess, would be meaningful, because then we can perhaps our performance evaluations will be more realistic than being realistic estimates as they are for now. That's one way to improve how accurately this platform represents a real system. But that alone might not solve the issue, because this frequency discrepancy is not just between the memory and the CPU. And by solving the frequency discrepancy, you don't essentially represent maybe the same latency also. Like if you're using other components, if there's one component you forgot to scale, then that's still something that you need to fix. So maybe a more general approach, maybe a different approach could make more sense.
Yeah, I can see that it would be necessary to come up with a kind of rigorous methodology to do the scaling.
Yeah,
but in principle, it can be feasible and show even better performance estimates or performance trends. Okay, yeah, that sounds very good. Okay, let me think if I have a couple more questions for you. So, yes, you mentioned that you need to do reverse engineering to figure out what's the mapping of physical addresses to DRAM addresses, right? So that's something that you have to do today. By the way, you mentioned RowClone and also RowHammer. I think you didn't point to any RowHammer paper or information related to RowHammer. I would like to mention now that for anyone who wants to learn about RowHammer, they can check in our website the SoftMC course. I think that there are some interesting lectures about RowHammer there. But yeah, you mentioned these two methods to perform this mapping between or identify or reverse engineer this mapping the physical addresses to DRAM addresses. But in near future, hopefully, where processing using memory systems are more established, so who would need to provide the information? How could the OS obtain this information? Do you think that reverse engineering could still be necessary, or at some point it might be possible for memory controller to provide that information to the system? or the DRAM chips themselves?
Yeah, so I think there are, I mean, two ways going forward. The first, I think, is just no one does anything, so no one discloses anything, and people still try to reverse engineer stuff. Basically, maybe I can talk about this. This wasn't in the slides, but another way to reverse engineer that mapping is to use timing sidechains. What you try to do is you try to find bank bits of the address by randomly generating addresses and testing if two back-to-back accesses to DRAM result in bank conflicts or not. If that's a bank conflict, you can understand that it's a bank conflict because it will take more time than other requests. And that way you deduce the bank address bits, and then later you can do the same again inside the bank, because now you know the bank bits, and you can understand the row bits and the column bits. But all of these works, I think, assume that there is a linear relationship between the physical address bits and the DRAM address bits. So that basically means that multiple bits are XORed to form one bit on the DRAM address. But if this assumption is broken in future generations of DRAM chips, or not DRAM chips, I mean the processors, then it will be more tricky to reverse engineer that. And maybe if the vendors wanted to, they could essentially make that information more proprietary, but that will work against what you discussed. Like if we have more PIM more common everywhere, this would work against that. So there's needs to be somehow a way of communicating that information, or the vendors should communicate that information somehow to the system, or they can still keep it proprietary if they implement hardware mechanisms and expose this only through some specialized instructions or some hardware functions or functionality they have. Right. I guess I'm talking about in our case, maybe I'm talking about the allocation mechanism all in hardware. If you want to do it from the software side, I think you need that information, and then the only option you would have is to either reverse engineer or use, if the information is made available, use it that way. But I guess I guess foresee that will be the case. So this probably will not be a proprietary information after some point.
Mm-hmm. Yeah, I agree with you. I think that I mean, in the end, makes sense, right? Because at the moment we're only able to let's say try or experiment with this processing using memory techniques by playing, let's say, some tricks that we or other researchers discover over time. It's like playing with the timing parameters, but hopefully at some point we will have DRAM chips supporting like these operations natively, right? It's I don't know, maybe in the way that the original RowClone paper, for example, proposes, or the Ambit paper with a specialized or a special row decoder, and so on. If that's the case, and someday we see those DRAM chips, hopefully there will be a, let's say, established way of providing this information to the system.
Yeah. It's especially if you want to integrate it, everything into the system as much as possible. So what we did here, the case study we have done, we assumed that RowClone would be tightly integrated with the rest of the system, right? Like we would do allocation, we would be copying. So what we worked for essentially is using RowClone when the RowClone pages are your virtual pages. If you don't want to integrate it as tightly, maybe you don't, well, maybe you can, you're not as constrained, and then you don't have to expose much information. But I guess it is more general and beneficial if you integrate it into the system as much as possible, because then the programmer can use it easily. I guess the case I'm comparing this to is somehow dumber somewhat dumber implementation of this would be dumber in the sense that it's simple. You would allocate some physical memory for this types of operations, and then you won't have to worry about coherency and potentially mappings. I could tell the programmer that you have to work on this addresses. You fill this part with some data. Tell me when I need to do the row clone operation, and then I will do it for you. Type of like an accelerated integration. But that's, I guess, not fun to begin with, and the second is maybe not as useful.
I see. Okay. Yeah, I guess I don't have much more. I think, well, you mentioned at some point that PyDRAM has also D-range implemented. I think you didn't present anything about D-range, but the details can be found in the paper, right?
Exactly, yes. So I didn't talk about it because I think this would already be too long, but to summarize, we implemented D-range. D-range is a DRAM-based true random number generator, and how it works is you access DRAM cells with reduced activation latency, which is TRCD. So it's the time window between the activate and the first read command you send to the DRAM row. And that results in metastability in some of the sense amplifiers. And if you interrupt the sense amplifier during the sensing process, you will get random values on the bit line. And what we did was to integrate this mechanism into PyDRAM. We implemented some random number buffers in the memory controller. We exposed it through the instructions that I presented at one point to the rest of the system, and we observed that we can generate two random numbers at 8.3 megabits per second, which is comparable to what D-range already shows. Although D-range is like D-range study is like in a more maybe not optimistic, but a more realistic, a representative case. And there are some optimizations we can do in our case to match D-range's throughput. Basically, that's the conclusion we have in the paper. And the basis we have there is useful for both future D-range studies and future studies that will use reduced activation latency. So that can be DL-POF that I talked about, or other techniques that benefit from heterogeneous activation latency in DRAM. That's a quick summary. Sorry for that.
Okay, yeah, very good. Thank you for the summary. Okay, I think I don't have any other questions. I think that, I mean, you did very well with the explanations and also all clarifications later. One last thing I would like to mention, because you mentioned as well that PyDRAM can be useful to implement SynDRAM, that is an end-to-end framework for processing using memory to enable even more complex operations than the ones that are proposed by Ambit, or you mentioned here that the ones that were already tested by the compute DRAM work. With SynDRAM, it's possible to go one step further and have more complexity in the operations. And I would like to mention that next Thursday we will have another invited lecture about SynDRAM. For anyone who already wants to get familiar with SynDRAM, Ataberk showed one slide about the previous Safari Live seminar about SynDRAM. In the end, so in SynDRAM, just very briefly, you mentioned as well that the transposition unit. This transposition unit in SynDRAM, as we will see next Thursday, is in the memory controller. You could also implement that in the FPGA, right, near the memory controller.
Yes.
Assuming that there are enough resources, of course, in the FPGA.
Sure. Yeah.
Okay. Yeah. Very good. I mean, it's probably not the only way of doing transposition as well. Even in software-based transposition can be done. It's something that we, for example, talk about when we presented the PIM architecture, because there these transposition not exactly the same, but necessary transposition for the DRAM chips, for the admin chips, is done in software, and it's also relatively efficient. So I guess that in hardware could be even faster. Okay, yeah, I think that's also all for my side. I don't know if you want to add anything else.
No, I don't have anything else.
Okay, very good. Yeah, again, thank you very much for the nice talk, and yeah, I guess I'll see you in the lab soon.
Yeah.
And thank you everyone for your attention. I hope that you found the lecture useful, and see you next Thursday.
Thank you, Juan, for this opportunity, and see you.